you here. So I'm Catherine Zhao, and I'm assistant professor in computer science. So the topic I'm going to talk about today is when attention meets big data and deep learning. So here's the outline of today's talk. I'll start with the introduction, and then I'll talk about large-scale attention experiments and deep learning for attention prediction and visualization. So here is a very brief kind of slides summarizing my research motivation. So broadly, I'm interested in developing artificial visual systems that show the same degree of autonomy, adaptability, and speed as humans. And I'm also interested in developing experimental methods and machine learning techniques to address some fundamental questions in visual neuroscience and to develop clinical tools that relate to vision or mental health. And in the rest of the talk, I'll be talking about attention and show why attention is important in these tasks. So attention has evolutionary significance. The input to our retina is simply too much more than our brain can handle in real time. And we have to decide where to look at in order to react in real time. This is true for many organisms, and it's true over many, many years evolution. And this is also true for machines nowadays, with overwhelming amount of visual data, as you can imagine. So it could benefit artificial agents like robots if it's able to attend to critical information. So it could help it to explore and navigate with greater autonomy in real-world environments. It also causes all sorts of economic interest for people who would like to know and control your eyeballs. Like the advertising industry. They want to know where you look at in billboards, in newspapers, in web pages, and so on. And it could also benefit political or economic or social events. So we know that Steve Jobs was very good at. So when he was on stage, he was very good at attracting people's attention to what he wants to show or sell. So attention is important in both humans and machines. So next, I will introduce a number of genetic challenges in attention studies, and also show why attention wants to meet with big data and deep learning. So we know that big and deep are popular and promising these days, but why for attention? So the first challenge is what we call the semantic gap. In the last 30 years, predicting where people look at has been an active area of research where a couple 10,000 papers were published and so on. Yet conventional models, they rely on pixel level, kind of low-level information that highlight contrast or edges in an image. Whereas humans, as you can imagine, they would look at consistently on important semantics. So this is a so-called semantic gap between machine prediction and human behavior. So underlying this challenge and the motivation of many modeling efforts are what I think the fundamental challenges in computer vision. For example, here shows the variance challenge. The appearance of the same category could be drastically different in real world. And objects of different categories, hundreds and thousands of categories, they could attract attention. So there's also the scalability issue that we want to address in modeling. On top of that, humans might attend to some emotional objects rather than more neutral objects. And this also brings in the sentiment gap, as we want to kind of teach machines to do as well. So the second limitation challenge is relating to data collection. Unlike other visual annotations, a typical method to record attention data is with this customized eye tracking devices, which usually costs somewhere around $20K to $50K. And how it works is that subjects usually sit in front of screen and watch images or videos displayed on screen. So a customized eye tracking device would map the eye image to the image coordinates on screen, thus recording gaze during viewing. So the reliance on this device makes the task difficult to scale. So you could imagine a graduate experimenter needs to invite subjects one by one to perform these experiments. So this is also the reason why attention data set is tiny compared with other visual data sets like segmentation or recognition, which are crowdsourceable. So the next two works that I'm going to present feature in big data and deep learning, and were proposed to address these challenges. So we designed enabling method, new psychophysical method to record attention data in large scale. And we also develop new deep learning algorithms that are able to automatically learn high-level object and semantic-related features to fill the semantic gap. So I will also briefly introduce our open platform and a demo page. All right, so next I will be telling you about our enabling method for large-scale attention data collection. So as a data scientist and experimentalist, I have been long thinking about and motivated to see attention research in large scale. So this, I believe, could benefit modeling, for example. Deep learning favors big data. And also, it would enhance the understanding of attentional mechanism, especially at the individual level. So imagine if we only have like 10, 20 subjects. The study of quite a few exciting problems, as I will be mentioning later, is quite limited. So with the method that we develop here, we're able to enhance the usability and scalability of attention experiments. And the data set that we collected with this method is several orders larger in magnitude, with a much wider distribution, geographic distribution, less cost and faster in data collection. So this slide summarizes this method. And we see that the stimuli encodes visual acuity drop-off as a function of retina eccentricity. So we fit it to the exact curve of our retina, and only the central point is reviewed in high resolution. And subjects were instructed to move their mouse to review where they find interesting. So this is a free viewing task where each image was shown for 5 seconds. So they move their mouse to review objects of interest, very similar to as humans move our eyes to review objects of interest with phobia to be reviewed in high resolution. And I have a demo here where this is what our online subjects see. So they just move their mouse or touch a touchpad to where they find interesting and want to see in high resolution. So this is free viewing task where they are only instructed to freely explore the scene. But the same mechanism could be used for other tasks, like we have a visual search paradigm, which is probably less boring for kids. So they are asked to find some objects in a scene. But the underlying mechanism, the method is essentially the same. And this could also be, this also works in touchpads, in mobile phones, and so on. So now we are able to record attention data in, with general purpose devices like computer mice or touchpads or cell phone. So this allows us to kind of to be ported in crowdsourcing platforms, and we use AMT to collect attention data on 20K images with 60 subjects each. So in comparison, a typical current eye tracking data set contains image around several hundred to 1,000, around that range, and with like 10 to 20 subjects for each image. So this kind of increased that the numbers substantially, And as long as we invest more to AMT platform, these numbers could just easily grow. So then, of course, a natural question is that how the data resemble eye tracking data, given the two different ways of data collection, one using eyes and the other use mice, for example. So we performed several comparisons to basically compare the data that we collected. So here, the vertical axis is the area under the curve to kind of quantify similarity with eye tracking data. And the horizontal axis are the blur level of the final saliency map, which is a common practice for model evaluation. So here on top, the green curve shows intersubject variability of eye tracking data. So that, I think, is kind of used as a baseline, as this is the degree of different human subjects, say 15 subjects, how they agree with each other in where to look at in natural scenes when recorded by eye tracking devices. And then the next two curves show the mouse-eye agreement for experiments in lab and experiments with AMT. So before we port the experiment to AMT, we performed controlled experiments in lab to make sure that the method is valid. And then this group of curves show model prediction evaluated by eye tracking devices. And we see that the mouse data are reasonably close to the eye tracking data. And further, we validated this mouse tracking data as a benchmark to evaluate attention prediction models. So we see that the rankings of the models are pretty consistent with those evaluated by eye tracking data. So we have actually shared all the data and also host a challenge. And the data is currently used by quite a few research groups over internationally. So basically, this is a first sort of big data, very useful for model training and evaluation. So we host challenge, to kind of facilitate attention and vision research using big attention data. A yearly challenge in CVPR, which is a reasonable computer vision conference. And also, we have a web page where you can explore examples of our attention data collected by the mouse tracking paradigm, and also with categorical labels on each image at the same time, we're able to explore them by category. So the last thing I want to mention here is that attention is not standalone. Humans make multiple fixations to understand a scene. So I think attention could be used together with other visual annotations that are more task-specific. So for example, segmentation treats all objects equally in a scene. But as we can imagine in natural scenes, some objects appear in background. So they are not equally important, essentially. And then our attention data could naturally rank all these objects, identify key components, and also convey some social cues. For example, here in this image, people are looking at this watch. It's not because that faces are generally less important than a watch. In fact, humans are attracted to faces most strongly and rapidly. But here we look at this possibly because it's a advertisement scene featuring certain watch brand. And also, people look at this side of the people more than this side of the people. And I've asked the groups of people to discuss why, and many say that possibly because here on this side are some young, beautiful women, or because they are interacting and talking with each other. So these are all important social cues that we would also like to teach the computers to learn, when for attention prediction or for other visual tasks. And also, since here we have the statistics of 60 online subjects, it also allows us to study exciting questions regarding attention, like gender difference, whether men look at this side more than the other, or cultural differences, age differences, and so on. Just out of curiosity, we group them, the subjects, into different genders, and it seems, both groups look at this side more than the other. So we have also built, with some increase and demand of using our mouse tracking method. So we've built an integrated online platform for large-scale behavioral data collection. So besides attention experiments, we also include templates to, templates with rich functionality, including object labeling and segmentation, semantic and sentiment annotation, and common survey templates. So besides featuring in large scale, this platform also highlights the use of general purpose naturalistic images that are ecologically relevant, but are difficult to use or challenging to use for conventional cognitive or neuroscience experiments due to their complexity. So here we include, ready-to-use templates. Experimenters need only to upload the image stimuli that they want to test. They could, design various questions, tasks, instructions, within this templates. And it's also integrated with common platforms like AMT for easy management and payment issues, for example. And we also provide functions for data visualization and analysis, so pretty easy to use in general. So for example, we have used this platform to collect a comprehensive set of data for sentiment analysis. So here we annotated a rich set of high-level attributes, like those describing a scene, including, say, aesthetics of the scene, informativeness, naturalness, and also those describing emotions like happiness, whether it evokes a feeling of sadness, awe, and so on. So besides, all right, never mind. So we've also collected attention data at the same time. So then this allows us to, study questions cross modalities, like correlate attention with emotion, with semantics, with scene and object categories, and so on. And this is just an example. So we envision that with this enhanced, scalability with the mouse tracking paradigm and this open platform, we could, this could possibly lead to many new and exciting applications and studies. All right, so lastly, I will talk about deep learning. I will talk very briefly about model and the performance, and then I will spend some time discussing you with feature visualization. So for myself, the motivation of developing deep learning algorithms for attention prediction is beyond the popularity of deep learning. So that is basically starting from the realization of the semantic gap. And then, deep learning seems like a very, promising computational tool that are able to automatically learn scalable, high-level image features from the data. And from there, we started to use deep learning, and we've got pretty good results. So, so here is an example that shows the traditional challenges of, modeling, realizing attention in machines. So as you can see here, previous methods all fail to predict where people look at, and they highlight all over the image, as they are essentially pixel-based. And our model based on deep learning is able to identify where people look at in a pretty accurate way. So here we don't use any pre-trained object detectors. The method that, the features that we learned from deep learning are scalable to, hundreds and thousands of categories in real world. So we have a demo page called silicon.net/demo. And we'll be updating this page with, better and better models, better and better data and so on. So you are free to explore the page here and see how our model predicts where you're going to look at. So very briefly, here are some examples from public data set. And while a conventional method would possibly highlight the edges and the texture here, our model is in general pretty good at identifying important semantics in a scene. So like here, there are also some kind of background that we don't want to highlight. And so the model generally performs pretty reliable. And you feel free to upload any of your own photos or images from the internet. So very briefly, this is the model overview. I'm not going to details, but essentially the model highlights a few things that are new and particular to attention prediction. So for example, we highlight peripheral vision, the low resolution part of the image. And we use saliency-specific objective functions for the first time to learn features particular to attention prediction with backpropagation. And also, we designed a fully convolutional architecture to train the model end-to-end and for pixel-wise efficient prediction. So there, of course, are a comprehensive list of intra-model and inter-model comparisons. So here, just very briefly, so this slide kind of summarizes the intra-model comparisons over 3 popular deep learning architectures. So I would only like to mention that the new components that we designed for our deep learning model, particularly to solve the attention problem, actually helps to boost model performance. And if we use off-the-shelf deep neural network of features for this particular task, it's actually not very helpful, as shown in the leftmost bars. And they don't improve performance much over the previous prediction methods. So we also compared it with the state-of-the-art models over commonly used eye-tracking data sets. And we see that while the improvement over the last 15 years are pretty incremental with with a few percent, here our performance is, it kind of jumps a lot toward human performance, about 70% toward human performance, as indicated by the red line here. So this kind of sets a milestone in prediction by proper design of deep learning algorithms for the prediction. All right, so in the last few minutes, I would like to discuss with you, some feature visualization results, hopefully to kind of, deriving some insights as of what deep learning kind of outputs and why it increases performance for those model predictions. And so in this example, so here are some neurons that we visualize from the deep layers of the model, as I just showed before. And these are the neurons that, that encode patch that people look at. And we see that these patches correspond to semantic and object-related information, like encoding screen, encoding faces, and head-shoulder patterns. So other neurons that have a high weight in predicting attention also encode text, rounded objects, and so on. So in contrast, neurons that don't attract attention do not have a clear semantic meanings here. And also in a recent study where we use deep learning to study sentiment, we also visualize neurons that strongly correlate with different emotions. And as you might feel, these neurons, they encode patches relating to happiness, where they show kind of colorful flowers, celebrations, or a blue patch with warm and bright light, things like that. And of course, these neurons encode emotions. They strongly correlate with emotions of sadness, and they kind of show grayish color and shabby appearance. And as one of my students always mentions they also include, those long and straight lines, possibly evoking the feeling of loneliness or hopeless, kind of things. And these neurons correlate strongly with the feeling of awe. So some patches encode kind of certain spatial layout, like long and straight shape, like a tall building, and while it's viewed from bottom up, or it encodes like serene natural scenes with wide viewing angles and highly saturated colors. And lastly, we have a recent work that, use deep neural network to identify people with autism from controls using their attention. So in general, this is a very promising area of research, as attention network is so pervasive in our brain. So by looking at the atypical attention patterns in humans, it's possible to identify, to distinguish people with various neurodevelopmental disorders. And here is just an example, and I don't have details to tell you about the method, but what I find most interesting are the visualizations. And here's one slide about the visualization. So if I ask you, which patterns, which role correspond to attentional preference of autism and which role correspond to controls, would you be able to identify them? So these are the neurons that are most, most kind of suggestive of, one type of subject from the other. Mm-hmm. Controls.
You're asking us to guess which one?
Yeah, which role are, the neurons that are most likely to distinguish autistic people?
So I would say the top row.
Very good. Very good. I mean, so basically, so the autistic group are most, the neurons that are, most likely to distinguish them kind of represent mid-level structures like edges, shapes, repetitive patterns. And of course, these two neurons are quite confusing, right, because they kind of encode social information. But if you take a closer look, we actually find fixations mostly around hair or mouth regions, kind of suggesting a tendency to avoid eye contact. Right, very good. And in contrast, control people, they're mostly distinguished by social cues, like text, signs, faces, including the eye regions, upper bodies, limbs, and so on. Okay, so I'll stop here. Thank you very much for listening.